Okay, this video is going to be about number systems. What are number systems? They're basically just a method of keeping track of numeric quantities, things that are countable, right? There have historically been lots of different ways of tracking that. One of the most common is, using your fingers to count, using hash marks, right? Where you have, a little bar, 1, 2, 3, 4, and then the fifth one might cross over that. But that gets a little messy once you get beyond, 20. Right? It becomes a little bit difficult to keep track of. There have been lots of other number systems. The Roman numeral system is a famous one, but it's compared to what we use today, it's a little difficult to do things like addition and subtraction. The digits don't line up. Okay, so basically what we're going to be talking about today is the number systems, the Arabic number systems, right? So we use base 10 is, if we don't specify otherwise, that's the assumption that we're always talking about base 10, right? And that comes from 5 fingers on each hand, so that's 10. So base 10 is the natural human number counting system, right? So what does it mean to be base 10, right? Another word for base 10 is decimal, okay? Base 10, obviously there's something to do with 10. Well, what makes it base 10 is the number of symbols you're allowed to use, right? So in any given digit or place value, we can use one of 10 digits, right? 1 through 9, there's 9 digits there, and then if you add 0, that's the 10th one, right? So any of these are fair game in a particular place value, right? So in this example, we have place values, and this is a 4-digit place value. So here, x0, x1, x2, x3, these would all be one of our symbols. Okay, so these are just kind of, placeholders. So in base 10, the way it works is this first position here, all the way on the right, is the 10 to the 0 place. Right? If you recall, raising anything to the 0 power is 1. So this is the ones place. And you probably remember this from elementary school math, right? The ones place, and then we have the tens place, and the hundreds place, and the thousands place. But the reason that this is 1, 10, 100, and 1,000 is because each place value, the exponent is increased. So you start with the base, so this is base 10, so we start with the base, and then the first one is 10 to the 0 power, or 1. The next place is 10 to the first power, which is 10. The next place is 10 to the second power, which is 10 times 10, or 100. And this is 10 to the third power, 10 times 10 times 10. It's 1,000. Okay, so that's where our places come from. And when we move on to number systems, we do the exact same thing. But the important thing to remember is it's a base to a power. So the 3, for the x3 digit, it's that power. Right? So this is actually the 4th digit from on the left, right? So it's 10 to the 3rd power. Right? Because the first one is always 10 to the 0 power. Right? So we'll do a quick example. We all know how to use decimal, but this example kind of breaks it down in a way that we can understand when we move on to other number bases. Right? So the simple example is 2,781. So here we've placed, one of our 10 symbols in each one of these place value positions, right? And it's really simple to convert this to decimal, right? I know it's already in decimal, but we would do this with any other number system to convert it, right? So we take that digit and then we multiply by the place value, right? We already saw that the place value is the base raised to the position power, right? So this is 2 times 10 to the 3rd, right? So that's going to be 10 to the 3rd is the thousands place, so that's 2,000, right? Plus 7 times 10 to the 2nd, plus 8 times 10 to the 1st, plus 1 times 10 to the 0, right? So for each one of these, we're pulling it down and then multiplying by the place value. So we pull down the digit and multiply by the place value. Pull down the digit, right, and multiply by the place value. And we add all those up. And that's all we do. So this down here is I'm just simplifying the place values, right? That's the 1,000. This is the 100s. This is the 10s. This is the 1s, right? And then I'm doing the multiplication, right? So this is 2,000. 7 times 100 is 700. 8 times 10 is 80. And 1. And we see if we add all of those up, we get 2,781, right? Now, admittedly, that's back where we started, and it seems kind of pointless, but you'll see why this is useful when we move on to the next base. Okay, so the next base is binary. It's base 2. So what does base 2 mean? It means we have 2 symbols that we're allowed to use. It's still the same number system, and as far as it's the Arabic number system. When we run out of decimals over here, or digits, we have to add a 1 to the left-hand side, and then we go through all the digits again, right? And then we increment this one. But in binary, it's a little bit unique because there's so few items. There's only 2, right? So very quickly we run out of digits. But the same principles with place values apply as they did for the decimal values, right? We've got the position, right? x0, x1, x2, x3. And then we have the base raised to the position, right? So that's this is the place value. It's 2 to the 0 power. Anything raised to the 0 power is a 1. So this is a ones place. In all of our number systems, that first column is the ones place. But the next column is whatever the base is. So this is 2 to the first power. Well, that's whatever the base is. So that's 2, right? That's the 2's place. And then this is 2 to the second power, right? Which is 4. 2 times 2 is 4. This is 2 to the third power. 2 times 2 times 2 is 8. Okay, so we're seeing a pattern here. When we go from one place value to the next, we're multiplying by 2. So we start at the 1's place. If you multiply 2, you get 2. Start at the 2's place, you multiply by 2, you get 4. Start at the 4's place, you multiply by 2, you get 8. And same, you would go 16, 32, 64, 128, right? So it keeps doubling each place to the left. Now that's the same situation we had up here in the 10's place, right? Except we're multiplying by the base. We start with the 1's place, multiply by 10, 10's place, multiply by 10, 100's place, multiply by 10, right? So each place value to the left, you are multiplying by the base. Right? So, a simple example. Now we can only use the digits 0 or 1. So in our digit places here, I filled in 1101. And what we're going to try to do is convert that into decimal so we know kind of what that number means in terms that we're used to, right? We're used to the decimal number system. We all know what those numbers mean for the most part. So we do the same thing we did in the decimal example, right? We pull down the digit and then multiply by the base times the position. So this is 1 times 2 to the third. And then pull this down. That's 1 times 2 to the second. Pull down the digit 0 times 2 to the first, and then 1 times 2 to the 0. Right? And here we just simplify. Right? So 2 to the third is 8. 2 to the second is 4. 2 to the first is 2. 2 to the 0 is 1. And then we just multiply. 1 times 8 is 8. 1 times 4 is 4. 0 times 2 is 0, and then 1 times 1 is 1. So our final number is the sum here, right? So 8 plus 4 is 12, plus 0 plus 1 is 13, right? So this is the value of that number as a decimal. This is the value of the number as a binary number. These two values, they're represented differently, but the quantity is the same. If you see this number in binary, there's no difference to the actual number of items we're talking about. It's simply the way we're representing the data. Okay, so if I say 1101 in binary, I'm still talking about 13 things, right? This is just a different way of representing that idea. So number bases all can translate to each other, right? And so that's what we're going to try to do. We're most familiar with base 10, so we need to always be able to convert to base 10. And this is the system that we use for that. It's pretty easy. You just pull down the digit and then multiply by the place value. Okay, so let's try another number system. Hexadecimal. Okay, hexadecimal. This is base 16. Okay, so instead of base 10, we have, where you have 6 symbols, now we have 16 symbols. Okay, so we know that 0 through 9 are 10 symbols, and we're out of symbols, right? So what do we use? Well, we can move to the alphabet, right? And so these are an additional 6 symbols. So that's 11, 12, 13, 14, 15, 16, right? So that's a total of 16 symbols, right? So let's do the same thing. We have place values for the 4 digits, right? And then, so this is x0, x1, x2, x3. This is 16 to the 0. Anything to the 0 power is the 1's place, right? Anything on the right-hand side is the 1's place. Here this is 16 to the first, so that's the 16s place, and we just keep multiplying by 16. Now we see this number gets quite a bit bigger, gets very large in a hurry, right? So notice in base 10 this is just the thousands place, and we're already more than 4 times that now. Whereas over here in binary it gets big very, very slowly, right? We had a 1 here in this 4th place, and that is only 8, right? So comparatively, a 1 in that 4th position with binary compared to a 1 in that 4th position of hexadecimal is tremendous, right? It's only 8 in binary, but it's 4096 in hexadecimal, okay? So let's do an example. We have 1A8F, okay? So I put in those symbols for each place value, right? But one additional step we have to make here is we have to kind of translate what this means, what this character means, right? We know what a 9 means in base 10, right? But what does an A mean? Well, if we have an A, that actually means 1 more than 9. So if we were, converting what just this place value by itself means, it's a 10, right? An F would be, if that's 10, then that's 11, 12, 13, 14, and 15. Right? So an F is a 15. So that's what this line is doing here. It's just translating the digit to something that makes sense in base 10. Right? So A doesn't make sense in base 10. That's actually a 10. Right? F doesn't make sense in base 10. That would be 15 in base 10. Right? But then you do the same thing. Right? You pull down the digit and then multiply by the place value. Right? So the place value is 16 to the third. So that's 1 times 4096, right? This is, we pull down the digit, right? A translates to 10, so that's a 10 times the place value, 16 squared. And that's, let's see, 10, I'm not sure why I have a 7 there. That should be a 10. So 10 times 256, that is 2,560, right? And this is going to affect my final outcome, which is fine. And then we have 8 times 16 to the first, which is 16, so 8 times 16 is 128. And then we pull down the 15, right, which is what the F value is, and we have 15 times 16 to the 0, which is 1, and this is the ones place, right? So let me check my math here, since I had that little error. We'll open up Python conveniently enough, Python 3, and we'll just paste this in here and add these values up. Right, so that should be 6799. So 6799. So that is the value of this number, which is hexadecimal, 1A8F. The value as a decimal number is this. Now again, in terms of the actual quantity we're talking about, in both of these cases it's the same number of items that we're discussing. It's just how we're representing that idea. Here we're representing it with symbols that mean something different. The value of each symbol is different. Okay, a 1 here in this position means 4,096 things, right? Whereas a 1 here in the position, if it was base 10, would mean 1,000 things. A 1 here in base 8 means 8 things, right? So the overall quantity that we're talking about is the same, but it's just different ways of representing that idea. Okay, that's basically how you can convert any of these number systems into decimal form.